and today we're going to talk about the EVM. So the EVM, of course, is the Ethereum virtual machine, and it's a VM designed specifically for Ethereum. It's not as if we could have just picked any existing VM and tried to plug it into Ethereum. As we'll see, there's a lot of very Ethereum and maybe some economic and blockchain specific properties to it. Okay, so some of the EVM properties are that it's deterministic, so execution outcome is very easy to agree upon. And this is really important because if two different nodes had an EVM that came out with even the slightest difference in its computation, it could trickle up into different state changes, different block hash, and then we couldn't have consensus and build a blockchain upon that. It's also spam resistant, so CPU and other resources are metered generally at a very granular level. It's Turing complete. I'll give that a caveat, and we'll talk more about it later. It's got a stack-based design, and again, it's very Ethereum specific, so it can do things like query the block hash, account balances, and so forth. So real quick walkthrough of Ethereum's history, which is now almost 10 years in the making. In November of 2013, Vitalik released the white paper. April 2014, Dr. Gavin Wood released the yellow paper. 2014, there was an ICO that raised about $18 million. 2015 was the initial release of Frontier. This was the first launch of the blockchain, and it was very bare bones. Initially, you couldn't do anything but really produce blocks. And it was proof of work initially, of course. Later that year, it was thawed, so they allowed for transactions to be sent. And the difficulty bomb was introduced. So this was, since it was proof of work, they wanted to make sure that the miners had an incentive to keep up with changes and not fight them. So they introduced this artificial difficulty, which would go up and reduce their mining rewards, basically. In 2016, there was the DAO fork and hack. We'll talk more about that later. And then there's a period of time where there was a lot of optimizations, opcode tuning. Of course, the difficulty bomb had to keep being delayed as there were hard forks. More recently in 2020, the staking contract was deployed and the beacon chain launched. 21, we saw EIP 1559, which we'll talk a little bit more about. 2022 was the merge. We went proof of stake. And recently, staking withdrawals have been supported. So let's talk about the DAO hack a little bit. Here's where I need, there we go, I could do that. Did that? Yeah, I guess that messed that up. Okay. So a DAO is a decentralized autonomous organization, and it's much like a business entity, except instead of being run by humans, it's run by code instead. But like any other business entity, it has assets and can carry out business operations. This leaves it in kind of a legal gray area. Now, the earliest DAO, or sometimes the DAO, was launched in 2016. It raised $150 million worth of ETH. And then later that year, it suffered a hack. And we'll go into the hack a little bit later, but in general, it was a re-entrancy problem. The community couldn't decide whether they wanted to undo the hack or not, and so this kind of produced two different camps. So there's a camp that said code is law, and that whatever the code does is what it does. And then there was a group that said, well, let's undo this just this one time. And so this resulted in a hard fork into two different networks. And so mainnet Ethereum today is the fork that said, let's undo it. It was really bad. And then Ethereum Classic is the camp that said, code is law, let's keep it. And so these both, of course, survive to this day. And so Ethereum is really kind of the first smart contracting platform, and it's had a lot of challenges along the way. So it's had performance problems. There have been opcodes that have been underpriced, and this has allowed for spam at times and a couple times even outright DOS. So it's been so bad that people found opcodes cheap enough to execute that they could just spam the chain to the point where it couldn't work anymore. It's had high gas fees. Since block space is relatively fixed, demand is really the only other part to that, and as it's gone really high, we talked about CryptoKitties the other day, it's gotten pretty bad. We'll talk a little bit more about EIP 1559, which changed that a little bit. Front running is a problem. I know we talked about that as well. It's had it hasn't itself had hacks, but a lot of the smart contracts deployed have. There's been problems aggregating contract protocols together, and of course storage bloat is a really big problem. We also talked about that earlier this week. And here's just kind of a list of some little things that are unusual about it. Everything is 256 bits, so more specifically, the word size is 256 bits. And so even if you allocate something like a bool, it's going to typically be 256 bits. There's no floating point arithmetic. Recently, there's been some addition for fixed point arithmetic. We'll look at that a little bit as well. There's this idea of revert. So if you want to throw an error, you can do so, but it's going to basically cause an entire transaction to revert its changes, except, of course, the cost of gas. And then reentrancy, we'll look at that a little bit more. And then if you need to allocate memory, there's no real hard upper bound on the amount of memory that the EVM will let you allocate. So there's actually an exponential cost to it. So every chunk of memory that you allocate gets more and more expensive along the way. Okay, so let's talk about gas. We said that it's Turing complete-ish. So I like to think of it as it has a Turing complete instruction set. So what does that mean about the halting problem, though? So the halting problem tells us that we can't, in general, know that that all smart contracts are going to actually stop at any point in time. There's nothing to prevent them from having an infinite loop, and there's no real way to know for sure that there is no infinite loop. And so obviously we can't allow for this. And so the solution is a gasometer. It's a way to prepay for every single opcode that's executed. And it looks a little something like this. So we start here, we grab the next instruction, and then we look up its cost. So every opcode has a cost. Some of them are dynamic and some of them are fixed. And then we make sure that we have enough gas left. And if we do, then we deduct the gas, execute the opcode, grab the next one, and then we run in this loop. So when we're executing smart contract code, we're in this tight loop right here. And then eventually we either are done with our smart contract execution or we run out of gas and we throw an out of gas error. And so this is nice because it's safe. It prevents unpaid work from being done. Since we check before we do every chunk of work, we never do any work that isn't paid for. And it's also deterministic. So there's no disagreement on when something should stop or whether or not it came really close to its limit or anything like that. It's always very deterministic about that it stops and when it stops. But it's very inefficient. So before, you can imagine just executing opcodes one after another. That would be nice and fast. But here we have to go through this big loop for every single opcode. And that can be things as small as adding two numbers together or pushing or popping something from the stack. And there's a lot of overhead in those small cases. So gas is the unit of account for EVM execution resources. And whenever you send a transaction or want to invoke the EVM, you need to specify a gas limit. And this is the maximum amount of gas that you're willing to spend. And you also need to specify a gas price, which is how much you're willing to pay per each gas along the way. And in order to get into the EVM, you need to, an account has to be able to pay for its gas limit times its gas price up front. And that's initially deducted from the account balance at the very beginning of a transaction, and at the end, anything that's left is refunded to that account. So EIP 1559 was a change that was introduced to improve the gas pricing mechanism. So we saw with CryptoKitties that things got so clogged that the only way you could get a transaction through was to bid higher and higher and higher on the gas price until eventually a miner liked it and would pick it up. And so there was just a lot of volatility. And so this was a way to change it to become an algorithmic gas price. So what it did is it separated out the gas price into basically a base fee and then a tip. And the base fee is actually algorithmically set. So every single block has a specific base fee, and this is what's paid by anyone who's paying per transaction. during that block. And then they may or may not pay a tip. We won't really get into that. And the algorithm is congestion-based, so as blocks are full, the price will go up, and as they're more empty, it will go down. And on top of that, miners are allowed to slightly increase the block space a little bit, so there's a little elasticity in there. So there's a lot of moving pieces to it, and it's been kind of fun to watch it play out over the last couple of years. Okay, so we said if a transaction exhausts its gas limit, then it's going to produce an out-of-gas error, and all the changes are reverted, except for the fee payment, of course. Now, this is a problem because an average user doesn't really know exactly how much gas they should pay for a transaction. And you can't just fix that because it might depend on how a transaction is executed. It might have a happy path that's really cheap and another path that's really long, and you don't really know which that's going to be. And so this is solved with an estimate gas function. And this is an RPC method that a lot of public servers offer for free, basically. And so when you submit a transaction, the first thing you do is, or the first thing your wallet's going to do is query the RPC and estimate the gas call. And it's going to do a dry run of the transaction, which means it's basically going to execute the whole thing. And it's going to record how much gas is used throughout the execution. And that's what it returns to you. So you dry run your transaction, and you get an idea of how much it's going to cost, maybe add a little padding just to be safe. It's going to be refunded anyway. And then you send your transaction and hope for the best. So this works, but there's obviously some caveats. First of all, it's run against the current state. So if you do a dry run and you like the outcome and then you send it, a few blocks later, maybe the state's different and it's not going to execute the same way. Maybe it uses more gas and you end up running out of gas. The RPC node you're trusting, they could lie to you. Maybe they don't like your transaction, and maybe they'd like to see you just waste some money on gas. So you have to trust them. Of course, you could run it yourself if you're running your own node. And it's also expensive infrastructure to run, and is potentially a spam vector. So if I'm running a public RPC node that serves this estimate gas endpoint, I could just send a lot of really heavy infinite loop transactions and cause it to do a whole bunch of work for no good. So Ethereum has a couple different account types. Both look the same for the most part. So they're both 160-bit account IDs, and they can both hold and send Ether, but they're controlled very differently. So these two account types are the externally owned account, which is really just a user-controlled account, and it's controlled through private keys by sending transactions. Its account ID is generated by hashing the public key. And it uses an incrementing nonce to prevent replay attacks. And then the other account type is the contract account. It's controlled by the mutable bytecode that we upload when we deploy our smart contract. And it can only ever do exactly what the code says. And its account ID is generated deterministically when the bytecode is deployed. There's a couple different ways to do that, but we won't get into that. So transactions are assigned payload that can only come from an EOA, and this payload tells the EVM exactly what it should do. So we'll look at a few of the transaction fields here. There's actually a lot more to it, but a transaction can contain value. So this is how much Ether it's going to send along with whatever it's going to do, and it can be 0 or more. It has 2, which is the target of the transaction. That could either be a smart contract that we want to invoke, or it can be somebody to send some money to. Input, so optional input data that specifies how a contract should be invoked, which function should be called, and what those arguments are. Or in the case of deploying a contract, it specifies the actual bytecode that's going to be deployed. And of course, gas limit and gas price that we talked about. And then a nonce. So every account, again, has an incrementing nonce. And this dictates, it prevents replay attacks, and it also dictates ordering. And then, of course, it has a signature, which presumably comes from private keys, so that proves ownership. And it also, you're able to recover the public key from the signature and the transaction itself. So a little optimization there. There is no from field in the transaction. It's just you recover that from the signature. And so there's a few different ways transactions can be used. You can, again, call a contract's external function, in which case the input specifies how it's called. You can create a contract, input specifies the bytecode, or you can do neither. And in all cases, again, if Ether can be sent along. So in the case of neither, this is how you send money to somebody else. So for a transaction to be valid, and in fact, before executing it, or even gossiping on the network, so we don't want to send out a bunch of invalid transactions to everyone, we do a validity check. And this includes a few things. So we first want to make sure that the gas limit is sufficient. So 21,000 is the minimum gas that any transaction can allow. And this basically pays for the basic processing of itself. So at the very minimum, it needs to be able to deduct the balance of the user, and this covers that, as well as maybe some like signature verification. And then is the signature valid? So we make sure that it's from a valid public key and that account has funds. And as a side effect, we get the public key and the account ID recovered from that. Can it pay for itself? And then is this valid? Is this a valid nonce? So is this the next nonce in the sequence, or maybe is it a little bit in the future, in which case we're just waiting for the next transaction to execute and then it can. If it's a really high nonce, like U256 max, then obviously we're never going to get there. So we would discard something like that. And again, these checks all come with overhead, right? So if you get a transaction, if somebody on the network gossips you a transaction, you want to really, really quickly make sure that it's at least going to be able to pay for itself. And if not, you want to discard it. You don't want to broadcast it on to your peers. So let's talk about opcodes and bytecodes. So an opcode is a single byte, and it represents an instruction for the VM to execute. The EVM is going to execute bytecode one opcode at a time until it's done, halts, or the gasometer runs out of gas. And so when you write smart contracts, the functions that you write compile down into this bytecode, and then we take these, aggregate them together, and push it up when we deploy our contract as the immutable bytecode. And so we have this big blob of bytecode, and we need to understand how we can actually use it. And that's what ABI is. ABI is Application Binary Interface, and it basically describes the bytecode, annotating where functions and other objects are and how they're formatted. So for a function, you would be able to know exactly where it is in the bytecode, how to call it, what its arguments are, and so forth. And so I'm going to pull up, I hope, somewhere up here. Am I clicking the right one? Right there. Okay. So this is just a random, I went on Etherscan yesterday, and I just pulled up a transaction, and I pulled up the contract that it went to. So just random. It turns out it's, I think, Uniswap, and this is the USDC pool, but that's not actually relevant. And so what we're going to look at first is some bytecode down here. So this is the bytecode that was compiled when compiled and deployed when the smart contract was deployed. And so embedded in here are presumably lots of different things, including functions. And it's certainly not obvious from looking at it how you would call these functions. And so that's where ABI comes in. And so this is the ABI expressed in JSON format. And so it looks a little gnarly too, mostly just because we're not pretty formatting it. But you'll see that it's got some inputs, and it'll tell you about like types. So there's presumably like some address in there that's a constant or something like that. And so in this case, we actually have the smart contract code as well. And so the way this works on Etherscan is you deploy your contract, and then somebody can come in and say, it's this code. And then Etherscan will go do a deterministic compilation of it and make sure that they come out with the same bytecode. And if they do, they'll say, okay, this checks out. I think there's actually a little check mark if I scroll up. Yep, right there. And And so it just means that Etherscan has been able to verify that this is pretty much got to be the exact source code that led to this bytecode. So we have the source code here. And so one of the things we can do is look through it real quick. So there's just this library that it uses. We come down here quite a bit further. Here we go. So here's contract uni. And you can see there's some storage items. There's some constants as well. So maybe that constant that we just looked at was this one. Who knows? And then we can come down here. There's some more storage items, vents. And then here's a function. So this is an external function. So we should expect to see it in part of the ABI. So let's look for set mentor. Okay, so we see it once there. And then if we go down, sure enough, here it is in the ABI. And so here we have name, outputs, blah, 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 payable is false, and then we see type function. So just to give you an idea of how all this comes together. So this is able to tell you how in the bytecode you can call this function. Now, again, if I were to create a smart contract and I didn't want to make my source code public, or maybe not even my ABI public, this is all you would have. And you probably wouldn't really have a good idea of how to interact with it. It would take you quite a while to reverse engineer that. So a lot of times you'll definitely see the bytecode. A lot of times you'll at least see the contract ABI, so people know how to at least call some functions on it. But this is a big open source community, so a lot of times you also have the source code. Go ahead. We got the mic.
So does the arguments and the variables need to be sized? We need to know the size before at compile time?
Yes. So at compile time, they're known. So again, like I said earlier, most things are 256 bits. So you'll just kind of see them chunked in there that way. There are some dynamic ones as well. But you do need to know them at compile time, and they'll also be part of the ABI as well. So in order to call them, you have to get all that right, because it's an EVM, it's stack-based, it's going to push and pop things off of the stack, and it definitely needs to have the right sizes when it does that. And types as well, yeah. Good question. Okay, so can I do that? There we go. Okay. So all contracts have a sandboxed state. This not only includes their bytecode, like we talked about, but it's also their contract storage. So if I'm a contract, I have my own storage, no one else can write to it, only I can write to it, and I can only do that through my code. There's some ways to change that up a little bit. We'll look really briefly at those. But for the most part, you are in full control over your own sandboxed state. So at a high level, there's two different ways to call a contract. One is through an EOA. So typically that, at least on chain, is a transaction. And that's how you would start like a chain of calls. You would call some specific contract. Now that contract might be able to call other contracts, and we call that messaging. And so if you're a contract, you might be called from one of these two ways. But it's always going to start at the root level with a transaction. There's a few different ways that contracts can call each other. We won't really go into the details too much, but there's a normal call, which is just, I'm going to call you, and you're going to work on your own state. There's a static call, which is sort of a safe way to call something else and make sure that it can't change its state. So you can only basically call read-only functions in this way. It's sort of just an extra safety rail. And then there's delegate call, which is, we won't get into it, but it's a way to call another contract, but then say you can modify my own state. So like libraries use this a lot. So you can call like a library function that operates on your state. And so this message object is always available when we're programming. If we have a function, we have a message object. And this gives us a little bit of context about how we were called. So it has the data, which is how the input data. For a transaction, that would be the actual input data that was sent in the transaction itself. It has the available gas. Different than the remaining gas. So when I call another contract, if I'm a contract and I call another contract, I can specify how much gas it can use. Message is sender, so that's who most recently sent this message. The signature, this is basically the function that it's going to call. We won't really get into that. And then the value, so you can also send Ether along with it. If I'm a contract and I call another contract, I can also send some Ether along with it. So Ether is actually this really, really big number. So there's a lot of different denominations of Ether, but when we're inside the EVM, we basically are working with this unit called Wei. And this Wei, and so 1 Ether is 10 to the 18 Wei. So it's a very big number. And this lets us avoid a lot of complications with decimal math, while also not having really big issues with things like integer truncation. And again, determinism is a really big property of the EVM, so rather than having to force people to use something like floating point math or fixed point math, which is not always fun to work with, we just use integer math and say that there's a lot of implicit decimal places behind it. And so officially, there's a lot of different denominations here. Here's just kind of a table of them. Inside the code, I think you can, there's a constant for Wei, Gwei, and Ether. So Ether is the one that you see day to day. That's what humans know as, ETH. Wei is, of course, 10 to the 18, or 1 over 10 to the 18 Wei. And then Gwei is often used for gas. So if you look at like a wallet and you're about to send a transaction, the unit that it shows you is probably in Gwei. So as far as programming the EVM goes, ultimately we want to get this bytecode that we're going to deploy with the contract that we've talked about. It is possible to just assemble your own bytecode. I doubt that's practical in any way. And there's also a low-level assembly that we can use. We won't look at that today, but there is at least one language that is specifically meant to do low-level assembly. So it's much more practical to use higher-level languages. And there's two now that have been, at least two now that have been specifically designed for Ethereum, or the EVM, and that's Solidity and Vyper. And we'll look at both of those today. So let's start with Solidity. So Solidity, like the EVM, Solidity was designed for the EVM, like the EVM was designed for Ethereum. And its syntax is similar to C++ or Java. It includes inheritance, including multiple inheritance. And it's sometimes criticized for being a little bit difficult to reason about. And that'll make a little more sense as we look at Vyper later on. So we're going to look at just some of the syntax of Solidity, and then we'll jump in and do a little bit of hands-on coding. So this is just super simple example. So we have contract. Contract is kind of like the class keyword in a lot of languages, except that a contract is a thing that gets deployed on-chain and it will have its own address, right? So anytime you declare a member variable inside of a contract, unless it's const, it's going to be a storage item. So in this example, if we were to deploy this on-chain, we would have a contract called foo deployed somewhere, and it would have an on-chain storage item called bar. You give it a constructor to initialize it the way you want, and this is called when you deploy the contract. And so when you deploy the contract, you have to call this constructor. These are what functions look like. So we use the keyword function. We give it do something, and then there's a few different keywords. So public is one. That just means that it's externally visible. And then we say that it returns bool. So this return type here is a lot like a tuple in Rust. And then we return true. Excuse me. There's a special thing called a modifier, which is a lot like a function. And what it does is it lets you basically specify a precondition or maybe an invariant that has to be true in order for for the function it attaches to be used. So here down here we have a function do some admin thing, and then we say that it's only deployer. Well, only deployer is a modifier, which looks a lot like a function. And so in this case, we require that the message's sender has to be deployer. Well, the deployer is a storage item, and it's set in the constructor. So whoever calls this constructor, or whoever deploys this contract, is going to call this constructor, and we're going to set the deployer to the message.sender. So in this case, what we have is a admin function that can only be called by the person who deployed this contract. Right, so again, we have modifier, only deployer, and then we see that down here. So the other caveat here is that this little underscore thing is basically going to embed the function there. So you can think about when we have only deployer, we take the body of this function and we put it right there. Question?
Do modifier has access to arguments of do something?
Oh, yeah, great question. Yes, so they do actually have arguments. So you see here we just have an empty parentheses. So we don't in this case, but we do. And actually that reminds me, these things can do arbitrary things. So this is a nice modifier, but it could actually do anything it wants. It could go delete some storage or self-destruct for all we know. So that's one of the reasons why it's criticized. And we'll see later that Vyper does not actually support it. And it's in part because they can do arbitrary things. And so you can also imagine if you're coming in and you want to understand what this contract does, or maybe you're auditing it, and you saw this only deployer, well, now to know what do some admin thing does, you've got to go track this down, see what it does, and keep up with it as you're reading through the code. Question?
This is a question from few slides earlier.
Okay.
When you do when you monitor scan, when you upload the code to verify, monitor scan, you can also get the Solidity code from the smart, it does a reverse engineering, I guess. Mm-hmm. So if you upload that reverse engineered code that is not the original, it will fail the verification? That's
right. So they use deterministic compilation. So if I take some source code and I do a deterministic compilation, I'm going to get exactly this bytecode and nothing else. If I change anything about that source code, I'm going to get different bytecode, right? So in some ways it acts a little bit like a hash or a one-way function.
So even if the instructions of the old code end up being the same, like if the code that I upload is different, it will fail.
That's the idea, is that if anything's different, depending on the implementation, maybe you could change a comment or something like that and it would be okay, but yeah, it needs to be the same source code is the idea. It certainly needs to do the same thing.
Okay, thanks.
Question in the back?
When we can take the bytecode and change it back to the ABI, and I see all the function names are there. So I guess that's in order for other contracts to be able to know what methods to call. So does that happen only with public functions? Are there non-public functions? Because I guess if those names change to something smaller, we could save block space. So
yeah, good question. So there's a few things there. First of all, you can't go from bytecode back to the ABI. You need the ABI is like an artifact of compiling it. So when you compile something, you take the source code and you get bytecode, and then you also get the ABI.
Oh, okay.
You deploy the bytecode, and then presumably you need to publish the ABI so people know how to actually call your function. Okay. There's one thing we didn't get into. I'll talk about it briefly. When you call something, part of the ABI specifies that you take a function signature, and then you take the catch-up hash of that, and then you take the first 4 bytes of that. That is the identifier for that function. So that's how you know how to call something. So you can't actually change the name. And so the name is actually compiled out, right? You don't see the name in the bytecode. So the name itself, other than the ABI, is arbitrary. And so making it smaller doesn't actually help for on-chain storage. Okay. And then one other thing. There's internal and external functions. So these we saw earlier, I think public meant that it was an external function. So that's going to cause it to generate ABI for it. Internal functions are often implemented by just jumping, I believe. So rather than have an actual function and a program pointer increment on the stack, blah, 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 you just jump to them. I believe that's how that works. So, but the main takeaway is that internal functions aren't going to end up in the ABI.
Okay.
Question right here.
Just for completeness, there are like kind of rainbow tables out there, which are just like mapping from function to selector to the bytecode. So because function names are usually very similar, so as deployer or set deployer or mint or whatever, so people are just like hashing it with this cache whatever. And so the selector is the same for every freaking bytecode out there, and people are scanning your bytecode if there's like a min function on it or whatever.
Yeah.
So people don't need the ABI to interact with your smart contract at all. And so don't feel safe if you ever not like upload your bytecode or whatever and think no one can invoke this and read your smart contract. People are doing it.
Yeah, that's absolutely right. You should not upload your bytecode and assume that people won't figure out how to use it. On top of rainbow tables, you could also do a dictionary attack because most functions are going to have, English words in them and so forth. So yeah, good point. Okay, so we have an important keyword called payable, and this affects functions. So a function can receive ether along with its message, provided it is actually annotated as payable. So in this case, we have this silly contract that's going to keep up with how much received, but it's not actually going to do anything with it. So in effect, this is like a black hole. We send money into it, and it keeps up with how much money it's burned, but it's not going to actually do anything with it. And this is, of course, the keyword payable. So let's look at some of the types inside Solidity. So there's two different buckets of types. One is called a value type, and these are similar to like a lot of primitives that you'll see in a lower level language where they're actually on the stack. Their value is stored on the stack. Question in the back? Go ahead. Oh, yeah. Whoever's got the thing.
Hi, could you please explain more in detail to payable?
Sure, yeah. Let's back up real quick. How do we do that? Go that way. Okay.
Because like what I don't get is how much ether would you pay?
Oh, gotcha. So message.values, yeah, so that's a good question. So here we see that message.value is the amount that was sent with it. Now, this contract isn't responsible for doing the actual accounting for it, right? So every account in the EVM has a value associated with it, and the EVM is going to make sure that that's updated. So if somebody called this and they sent 10 ether, the EVM will make sure that this account now has 10 extra ether. So when we do this, we're just simply accounting for the fact that we got 10 extra ether, but it's the EVM that actually does, the account balance changes.
Okay, thanks.
Yeah. Okay, types. So we have value types, and these are like a primitive that's actually stored on the stack, so its actual value is there. And that's in contrast to reference types where we store a reference instead. And so most of these are, well, all of these are fixed sizes, right? So we have the usual suspects, so we've got a bool, we have ints, and these can be up to 256 bits. But remember, the word size is 256 bits, so these all still occupy one word. So this 1 bit right here is actually wasting 255 bits. And then we also have fixed length byte arrays. So this can be bytes up to 32. I think I need to scroll down. We also have this fun type called address, and we can assign an Ethereum address to it. So this is an Ethereum address with 40 hex characters here. If I were to delete one of those, it wouldn't be valid. It has to be exactly an Ethereum address. And this gets a couple special types. So one of these is balance. Another one is call, which we'll look at later. So it's a value type, but it has a couple special things. So this is one of those very, very like Ethereum specific features. We'll look at enums later. Those are also value types. And then here's just a quick way of seeing how this works. So if we declare an integer x and an integer y, and we say that y is equal to x, and then we change y, what we see is that x remained 1, y remained 2. And this will be in contrast to the way reference types work. Is at the bottom? Yep. All right, so reference types. So reference types are generally dynamic in size, or at least bigger than 256 bits. And we actually store reference to some other location. And this gets a little bit different than a lot of other programming where before you, or in other languages, you have like the stack and the heap. Here we have a reference that can point to other things. So it can be memory, but it might also be the call data that came from a transaction or a function call. Well, we'll get into that later, actually. I've got that on the next slide. So Here we've got a uint8 array. We give it a capacity of 3 and we assign it. Yeah, so this memory keyword is what I'm referring to, and we'll see that on the next slide. We have a mapping. So this one's a little bit weird because it actually can only point to storage. So here we can only initialize it by pointing it to for later, which I have right up here. So for later is something that is a storage item. So whenever you work with a mapping, you're necessarily working with storage values. And of course, we can index it by its key. So it's a mapping of key to value, right? And then we have dynamic length strings. And then we have structs, which we'll take a look at. What else do we have? And so we saw earlier how we assigned y to x, and that ended up with 2 independent copies. References don't work the same way, right? So here we declare something called array2, and we assign it to array, which I stuck up here. Okay, so we're assigning it to array up here, right? So we have this, we're assigning to this, and then what we do is we set its value at 0 to be 42, and then what we see is that both array and array2 are affected. And that's because they're the same reference. So I hope that's clear. And of course, be careful about that when you're programming. So data location, we started talking about this. Whenever you have a reference type, you need to specify where its data location is. And again, this is different than other programming languages. It's not just simply a pointer to some memory location. It has to be either memory, storage, so it can point to on-chain storage, in which case when you make a modification to that variable, you are changing the storage, or call data, which is a read-only area and it can avoid copies. So it's if you can get away with using call data, you generally should. And I'll just briefly go over this to elaborate. I feel like maybe this is a little bit heavy on the details. So we have this data location comes up here in function arguments. So we see that we pass in a foo memory. And then we also have, it can affect return types, and then it can also affect things inside a function. And so we can do some assignments. So if we have a memory object, we can assign it to another one. Storage values have to be initialized before they're used, and they can only be initialized to something that's in storage. So in this case, we had a struct. We'll look more at structs in a sec. And it's a storage item, so that's how we've assigned it here. And so when we do stored foo.I, we change this I variable, and that will actually change on the storage value. And then we can reassign a memory from a storage item, I think with the exception of mappings. But it becomes an independent copy. So in this case, if we make a copy, which is memory, right, and we assign it to foo from storage, which is a storage, we'd now get an independent copy. If we change I to 2, it's no longer changing storage. It's changing this memory version of it. And then of course we can return, in this case we returned from storage, which is kind of doing the same casting or whatever to memory here. We have enums, so this is pretty dry. We have a suite of for cards, and here's just the syntax for how we would declare and return that. And then we have structs, about what you'd expect. Again, syntax for how to use them. Okay. And so at this point, I'm going to do some coding up here on stage, and then after we do that, I have some coding that you guys can do, and then we can talk about it after that. Question first?
Yeah, Gavin. So you talked about, oh my goodness, I'm forgetting the name. In the transactions, well, we have functions.
Call data?
I'm just going to get technical and just help me go back to high level
Okay.
again. Can you just elaborate on the internal transactions and how that works? Is that like contracts calling contracts? What do the hashes represent in that case?
Yeah, I probably should have just put a slide together about this because it already came up. So when you call a function, by convention, You identify that function by its hash. So we take the function's actual signature as you see in code. So if you have like set value, a function set value, and then it takes like a bool something, you would take the set value parentheses bool. This is an actual string, right? Close parentheses, and then you take the catch-at cache of that, and then you take the first 4 bytes of that. And whenever we invoke the EVM, that's how it knows which function to call. So I think that probably clears up. I don't think I got all of your
that's
question.
the function call. I'm talking about internal transactions.
Okay. So there's the idea is that anytime you call a function, there's a message passed, and so the outermost transaction, I believe, is technically called a message as well. So you start with a transaction that's like the signed payload. The EVM or Ethereum knows that it's going to be able to pay for itself. That goes into the EVM, becomes a message. Every single function that's called gets this magic keyword called message, MSG, and that's the context that it knows that it can look at to understand how it was called.
Okay, so that means then in that case, when a contract calls another contract, it is effectively a transaction then?
It's not a transaction. So I like to think of a transaction as a very specific thing. It's a signed payload. You can see that you can derive the public key from it. You can make sure that that was signed by the private key. A transaction also has to have Ether attached to it, and that account has to be able to pay for itself. So kind of like when we saw the transaction validity, those things are all really important. Those things make a transaction. Anything else is not a transaction. So a transaction is something that is kind of outside the EVM, really. And it's so I kind of think of it as layers. There's the EVM, there's Ethereum. Ethereum does transactions. EVM does not, maybe with a couple caveats. But
okay, so maybe in Etherscan later on when you show us, you can show us like the semantical difference between why Etherscan says internal transactions when it's actually internal function calls.
okay, yeah, maybe we'll look at that. Yeah, I'm not sure exactly what they mean by that.
Well, when we pull up another scan page, we probably.
Why don't we do it real quick? Let's see. So I think it's not going to be here because this is a contract, but maybe real quick we can just like look up. Yeah, I know the word you're talking about because I've seen it before, but I'm like not getting the context. So I don't know, let's like pull up a block here. Transactions. And then like here's something that I don't know, the optimism sequencer. And so you would see here, is it like here in more details or no, that's not where it is.
I think it's a tab maybe on the top. There's state. And so there's, yeah, I guess it's changed since I last looked at it.
I'm kind of curious.
I'll look it up and I'll sync
okay,
back up
yeah,
with you
why don't we
offline.
talk about that offline? Yeah. Okay, so let's do some hands-on stuff. So first of all, oh, sorry, question.
Yeah, sorry. Could you maybe go into like opcodes and what was the history behind it? Like how does it work? Like Ethereum, like how did they agree on some opcodes? Like they were just, I mean.
Yeah, so first of all, the white paper introduced the first set of opcodes. And those opcodes, a lot of them are just basic stuff. Like in order to have a stack-based VM, you need certain opcodes like pushing and popping from the stack. So actually, like probably more than half of the opcodes in the yellow paper are just about how to push values to the stack or pop them off of the stack. And then there's also basic things like adding two numbers together. So the way that works is like if you want to call, if you want to add something at an opcode layer, what you do is you first push to the operands to the stack, and then you call the add one, and that's going to implicitly pop the two off the stack, compute the result, push it back onto the stack. So that's kind of how like the basics of it work.
So it's basically like rebuilding the computer, but in a blockchain way.
Yeah, it's probably pretty typical like VM development. Not that I have a lot of experience with that, but I imagine that's at the root, like what we've talked about right now is pretty basic VM stuff. Of course, there's other opcodes like you can query the block hash. You can query like the Coinbase address, so whoever mined the block or authored the block. So there's some very Ethereum specific stuff along the way. Josh, you've got a question?
Over here.
I bet he's going to answer your question.
Well, I just wanted to say one other thing. It happened before you were here, Stephen. We had the lesson about platform agnostic bytecodes. So the EVM is a platform agnostic bytecode, just like WASM that we looked a little bit deeper at, and we're going to look at again. So I just wanted to like make that connection.
All right, nice. Another question?
Yep. Is this working?
Yeah, we hear you.
So, as far as I understand, the EVM being a platform agnostic, you compile the Solidity code to EVM bytecodes, and then that runs on x86 architecture machines, right? Which are the nodes?
It's arbitrary, right?
Any
it
other
run
architecture,
on ARM,
yes.
or you do it by hand if you wanted.
Would it be efficient for for someone running a node to architecture hardware that specifically runs EVM bytecodes?
Yeah, that's a good question. So I venture to guess that yeah, you could probably come up with a good optimization by doing that. But what good would that do? Because you have a decentralized network, you can't assume that everyone is doing that. It reminds me a little bit about like Bitcoin mining, where we went from very generic hardware that would run it to now ASICs, and you have to run an ASIC, and that was like a keep up game. Everybody had to keep up. If you want to be profitable, you have to keep up with the hardware. This is a little bit different. You don't quite have that same economic incentive to keep up. Maybe you have a little bit, but my point is that the network itself doesn't have some means of making sure everyone can keep up with something really highly specialized like that. EIP 5059 introduced a way for block authors to slightly increase or decrease, kind of in a voting way. So when you, the block space, so when you author a block, it lets you bump it by, I think it's like 1/1024 is the amount that you can bump it up or down. And so everyone who gets to author a block has that little window where they can say, I want more block space, less block space, or the same block space. And so that's kind of the mechanism that we have right now to say, I think it should be bigger, I think it should be smaller. And so over time, you kind of get this voting mechanism where people vote for it to be bigger over time. So yeah, you could have an optimization like that, but then why would you do it? Like what's it going to actually accomplish? Yeah. A couple more questions back here. I think you in the back were first. Oh, no, I'm sorry, you were. Go ahead.
Okay, so when you talk about the data references, so the data have always to be in main memory?
So we have keywords, right? And one of them is memory. And it's different than other programming languages. So in other programming languages, you usually have the stack and the heap. In this case, it's just memory. It's not even necessarily one of those two things.
What I'm trying to say that, is there anything like when it runs out of memory, have to do anything with paging?
Good question. Paging would be like a low-level detail. That's how your machine would handle it. And it wouldn't be relevant here. So Ethereum doesn't actually, or the EVM does not actually have a memory limit. I talked about earlier, it has this exponential cost for allocating more memory. And so what that means is that it's going to ramp up really quickly. So you can't, you're going to have to pay more and more gas as you allocate more and more memory. And so that imposes kind of an implicit limit.
But because it's actually limited by the physical memory of the VM you run, right?
Yes.
So at some point when you handle a little bit bigger data, you always need some like maybe native mechanism for paging or something like this.
Yeah.
The reason I'm asking this question because we are trying to implement something like a query engine on EVM.
Okay.
So I don't know how to do it.
Okay, so you are going to run into memory limits in general. So one hard limit that you can impose at any block is you can take the amount of gas that a block can consume. So there's a limit for gas. We're just talking about that. And then you can see how much memory you could allocate with this exponential memory cost algorithm in there. And that'll put a hard limit on how much memory can be allocated. And it's not a lot. It's going to be probably in the megabytes range at most. Would be my guess. I pulled that number out of air, but.
Okay, so my last question, are there any query engine on EVM in the world?
I want to say yes, but I'm not really prepared to talk about that. Yeah,
okay, we'll take it offline.
Yeah, good idea. Okay, question back here.
Yeah, just a quick clarification. This probably is described more like in the white papers or whatever, but is like EVM the equivalent of WASM time when it comes to the executor?
I don't know that I can answer that question too well. So the EVM is an execution environment, as well as like the specification for how bytecode's done. I think WASM is more like the specification for how like bytecode looks, and then WASM time is more of the execution environment.
But wouldn't EVM be that execution environment?
It would, but it's also the specification for like how it's laid out and so forth.
And so like my question is, since like the EVM would contain, for example, many like many contracts, right? There wouldn't like, since there could be many contracts on a single node, there would be like some indexer in the first place to call specific functions on each contract, right? So it's like kind of an indexer at the same time, since it holds many subcontracts.
Well, sort of. So remember that when we upload the bytecode, we also need offline the ABI to know how to call it.
Yeah.
So you would find like an indexer offline. So like we looked at Etherscan. Etherscan is an indexer. It indexes the things on the blockchain and gives you information about them, but the EVM itself either doesn't know or would have to compute in an expensive way, right?
Yeah, it was more just like having many contracts on a single node, and like the execution environment, the EVM would have to know about each one that it holds.
Yeah, I see.
You see what I mean?
Yeah.
I mean, this is probably like just implementation details described in white paper, but I was just curious.
Yeah, you're right. So that is kind of a difference, I think. The EVM does have this idea of an account, and each account does have maybe some bytecode associated with it, right?
Yeah.
Whereas, other things in Substrate are things that we'll look at over the next couple of weeks. Those would just be a WASM blob, and you run that, right? Interestingly, Moonbeam which is an EVM compatible chain. It has WASM that is the runtime, but inside of that is the EVM. So there's almost kind of like layers to it there.
Multiple layers. Okay, cool.
But yeah. Come back up. Uh-oh, I don't think we did. Nope, we did. Okay. Okay, let's do some hands-on stuff. So first of all, I need to introduce you guys to Remix. This is what we're going to use to do some smart contract programming. And it has everything in the browser, which makes its dependency list really manageable. Just the browser, right? So it has an editor, compiler, EVM, and a debugger, all within the browser. So all you have to do is pull it up. So here's the URL to it. It's remix.ethereum.org. So I'm going to do some just real quick example programming up here. I encourage you to keep along if you want, but then I'll also ask you to do an exercise, and then after that we can talk about it. Okay, so I'm going to go ahead and pull up Remix, and I haven't thought this through too much. I'm going to have to can I rotate this whole podium? Maybe that's a bad idea. Okay, so I won't do that. A mirror, I can't do that either. Yeah, I could. I'm going to try this first. Okay. Well, let me just first introduce Remix. So here we're inside the browser, right? And this is, as promised, the full IDE for programming Ethereum. And so there's some tabs over here. That's how you get around to the different functionality that it has. And right now we're on the File Explorer version. I feel like that just did something that I didn't expect. Anyway, oh wait, we click it again. Okay, so we toggled between something. Anyway, this is the file browser, and so you can create a new directory, and you can create new files, and there's some other things like you can integrate it with GitHub. That's how you're going to create files and work with your actual programming. Then we have the compiler over here, so that's this one. And then when we actually have a file open, we'll be able to compile it, or try to. And then we have the deploy and run. And so here is where we actually have a EVM in our browser, and we'll be able to deploy to it and do some testing with it. There's also a debugger, and then we'll use this Vyper one later. But yeah, that's basically it. So what I'm going to do is create a new folder. We'll just call this PBA. Okay, and then create a new file, and we'll call this, we're going to do Flipper. flipper.sol. And Flipper is a really simple concept. We're basically just going to have a contract. It's going to have a single Boolean, and we're going to have a function that we can use to flip the value, and then a way to read it. And then we'll deploy it and play around with it a little bit. So I can rotate my laptop. That'll help. Okay, so we start out with a contract keyword, and we're going to call this flipper. Okay, and we're going to give it a bool, and we're going to call it flipped. Now, in order to initialize flipped, we need a constructor. But, well, actually, before I do that, I just want to demonstrate that this will actually compile. So if we hit compile, we can actually compile this. So we have the most basic thing here, which can't do anything, but it has this flipped value. So it's not useful for anything, but at this point we do actually have something that will compile. Okay, so let's give it a constructor so we can initialize our value here. So constructor is done like that, and we can actually give it a, I think for now I'm just going to initialize it to false. So we'll just say flipped equals false. Okay, and one cool thing that Remix is going to do is you see it's annotated this constructor with how much gas it's actually going to cost. So it did some dry run, like we talked about earlier, and it's decided that it's going to cost pretty much 37,000 gas. Watch what happens if I comment that out. Now it's a lot cheaper. It's only 12,000 gas. So this gives you an idea of how expensive it is just simply to write a value to the chain. It's about 25,000 gas in this case, 20 whatever. It's a lot of money, a lot of gas. Okay. So now we can also compile this, and we're good. We get a couple of warnings. I won't go into those, but if you do some programming, I would encourage you to. You'll get the same ones if you don't. If you just start out like this, take a minute to figure out what they mean. Okay. So now let's give it a function to actually flip our value, and we'll just call that flip. And this is going to be public. And it has no return value, so we don't have to specify returns. And what it's going to do is say flipped equals not flipped. Okay, and we can see here that we've got gas cost again. That presumably means that it compiled, but we'll go ahead and compile it, and we're good again. And so now we can go ahead and go down here and deploy it. So this is the deploy tab. There's different targets or different VMs that you can send it to. So you could actually use an injected one. So if you wanted to deploy this to mainnet Ethereum, you would specify injected provider, and maybe you have MetaMask or something that you would use. Question in the back.
Yeah, over here.
But to finish that thought, we're going to use one of the VMs that's inside the browser. That way we've got our nice little sandbox. Go ahead.
Yeah, just Benjamin here. Just quick question. Why there is two gas price indicated on the constructor?
That's a great question. I don't actually know.
Is it like the price for deploying the contract and the price for just running the function?
That's a good guess. Yeah, that's probably it. That's my guess, is that it's telling you if constructor were an actual function, that's how much it would cost, and then we can hover over it. Estimate. Oh, great. Creation cost and estimated cost, deposit cost. Okay, code deposit. Oh, that's telling us how much. The EVM charges per byte for deploying a contract code, and I think it's pretty expensive. I think it's 200 gas, and so that's what it's telling us.
Okay, so there is like the per byte amount and the execution amount.
Yeah, that's what it appears to be. And as you pointed out, you can hover over it and it will tell you more detail about it. Yeah.
Thank you.
Thanks. Okay, so we've got our deploy tab over here. We've compiled this, and so we can go ahead and deploy it, and we're going to do it and see what happens. So we got our green check mark. That's always a good sign. And then we come down here at the bottom, and we see deployed contracts, and it's a little subtle here because the coloring, but there's this little panel here, and it is the deployed contract that we did. We can toggle it, and so it has our one function, which is flip. And so we can flip it, and that's great, but now we don't have a way of seeing what actually happened. So let's add a view function. Function is flipped, and we'll call it public view. So view is going to specify that this is read-only. It can't modify state. And so one of the caveats of that is if we want to actually call this publicly, we don't need a function. We don't need a transaction to do it. It would make no sense to do that because we're not actually modifying state. So what we can do instead is query an RPC node and ask it to give us the value instead. So what we're going to do here is return flipped, and I need to also go up here and specify returns bool. Okay. So now we have what's it telling me here? Expected but got public thanks function. There we go. That looks better. Okay, so we have a function to set it, we have a function to view it. And so down here, as you're deploying contracts, they're going to pile up. So if I were to add one, it would get a little confusing about which ones they are. So I just like to delete it as I'm going along. So that's the old code, we got rid of it. Come up here, it compiled, we know, but I'm just going to press it anyway. And then now we can go ahead and deploy it again. Okay, so we deployed it, come down here. Look at our most recent one. So we have flip, and now we have is flipped. Also notice that the colors are different. So orange indicates that it's like a transactional thing. It would need to actually change state. Blue is telling us that it's view. It's a view-only thing. So we can start out by saying is flipped, and that's false. That's good because we initialized it to false in our constructor. And then we can hit flip, and we can come back here and see that it's true. Flip, now it's false, flip. Now it's true. Hopefully you guys can see that down here. Maybe I should have made the font a little bit bigger. Can you all see this okay? Okay. Okay, so that's just super, super basic smart contract. Any questions at this point? Okay, so now what I would like for you guys to do is, hold on, let me go back to this tab. So that's our flipper example that we just did. So I have an exercise for you guys to do real quick. So what I want to do is give you guys an idea of what I'm asking you to do and then step away for maybe 10 minutes or so and let you guys do it. And then at that point I'll come back and I'll start doing it myself. And then once you guys can start paying attention or keep programming yourselves, and then we can talk about it. Okay. So the exercise is write a smart contract which has a uint 256 storage value, and then write a function to multiply that with some function argument that the user specifies, and then interact with it. And I actually wrote this, can you force an overflow? And it turns out that very, very recently Solidity actually introduced overflow checking. Very recently. So what you'll need to do to actually make this work the way I want it to is introduce this pragma Solidity 0.7, and this will make it use an older one. So in fact, let me just go back here and I'll just show you guys here how to what that looks like. So just right up here at the very, very beginning, we're going to do that. Hit save, and what isn't it like? It requires a different compiler. Oh, it's telling me like I have to, if I do that and then compile it. Now it's happy or something. I don't know. I switched the compiler on it and it's not happy. So if you guys do that from the beginning, you should be okay. Oh, change the compiler up here. Well, it did. It did change it for me. Okay, and now we're good. Okay. Yep. Okay, so we'll go back here, and I think I had one other note that I wanted to. Nope, not that one. My hidden tab up here, which is this first one. Okay, sorry. Okay, and then there's a couple bonus things that you guys can do if you're just whizzing through this, and that is see if you can figure out how to prevent the function from overflowing. That's just a general programming technique, but then also write it as a modifier. See if you can write a modifier that prevents this storage value from overflowing. And this constant here might help you. This is U256 max, basically. So that's there should be 64 Fs there, basically. So, okay. All right, guys, let's go ahead and just go over this real quick. And then I want to just try to introduce you to Vyper in the last 15 minutes or so. Okay, so we have a contract here. I called it mole, and I gave it a uint256 value. And then we declared this constant, which is the maximum value for a 256 bit int. And we use that here so that we can just overflow it easily rather than have to multiply a bunch of times or something like that. So we initialize our value to be this max value. And then we gave it a get value so that we can query it. It's a view. And then we also have a function mole, which I added this no overflow. We'll talk about that in a second. And it multiplies value by itself plus the value the user provides. And so what happens is when we deploy it, we can come down here and get value. And we see it's this astronomically large value. And then we can multiply it. If we multiply it by 1, we should be safe from any sort of overflow. If we multiply it by 2 in this case, we get an error. And then it also gave us this thing to access the constant, by the way. Okay, so we've learned that we do have overflow checking in recent Solidity. So we set it to this old version, which didn't have overflow checking. And so what we found is that without any sort of explicit check, we can overflow a value. And the EVM will happily let us do that. So be cautious of that. That can absolutely cause bugs and result in lost funds or stolen funds. Okay, so what we did then is we checked to see if we overflowed. So the first thing we do is we just get the original value, then we do our modification, and then we make sure that the new value is greater than the old value. And it's as simple as that. So we can do that inside the function here, so that's what this commented out code does. But we can also put it inside a modifier here. So we created modifier, no overflow, and we just did the same thing there. Now, yeah, go ahead.
I think there is a problem with this implementation since it does not check if the U is a 0, since in that case the value is going to be...
Oh, that's a great point. Yep. Let's try that real quick. So we know that we can do 1 and we're safe, right? Because there's no overflow there. What if we do 0? Yep, you're absolutely right. And that's clearly not an overflow. So good point. We would want to make sure that U is not 0 or maybe allow for 2 different conditions there. So good point. We had another question? Same thing. Okay, good point. Okay, so no overflow. So remember, we do the same technique here. We use this require, which implicitly does a revert, by the way, if this Boolean condition is false, and it gives you this error message along with it. And then remember that the syntax for the modifier is that the function it's modifying is essentially inserted here where the underscore goes. Okay. In whatever time I have left, I want to go ahead and introduce Vyper. So Vyper is also designed for the EVM. It's very similar to Python, and it intentionally lacks a lot of the features that Solidity has, such as inheritance, in the name of being auditable or readable. And I pulled this out of their documentation. I think it's great. Simplicity for the reader is more important than simplicity for the writer. And if you've ever been in the auditing space, that's huge. You like readable code for sure. Code that does what it looks like it's going to do is really good. Okay, so compared to Solidity, we don't have inheritance modifiers, function overloading. It goes way out of its way to try to prevent you from doing recursive calls. I'm pretty sure you could trick that, but maybe not. And no infinite loops. So all loops have to have a range associated with them. So here's a very basic thing. So there's no contract keyword. Like Python, files are essentially modules. And so you declare something outside the scope of a function, and it is implicitly a storage variable. So here's very similar to what we saw with Solidity. We have a uint that we call bar, and then we have init is essentially a constructor. We pass in val, and we initialize it that way. This is what a function looks like, very much like Python. And we'll look at decorators. So this external decorator is, let's call it a decorator. We have do something, returns a bool, and it returns true. So there are only a few decorators, and this is it. So you can have external, which means it can be called externally, and it will affect ABI internal. can only be called within the current context. Pure can't read state or environment variables. View, again, like we saw in Solidity. Payable is the same concept. And it does not have modifiers that we just looked at. What it does instead is try to give you something that captures one of the most prominent use cases, which is to prevent reentrancy. And the way it works is you have the decorator non-reentrant, and then you give it some string here. And that's essentially going to create like a mutex with that string to prevent that particular string, to prevent reentrancy for that particular case. So we have types. This looks really, really similar. Bool are ints and uints. They can be 256 bits. It's the same concept there. They actually have fixed point here. They only have base 10 fixed point. And the advantage of this is that literals written in code don't suffer any rounding or truncation errors. Go ahead. Question back here. We got the mic, anyone?
Yeah, for the re-entrant, does that have to do with the replay attacks?
Yeah, if we have time, I'm going to go over the DAO hack, and we'll get a close look at that
Okay,
then.
cool.
Yeah. So let me try to whiz through this. So we have address again, same concept. We have fixed byte size arrays. It's pretty much all the same stuff. Bounded byte arrays. We have dynamic length, but fixed bounds, strings, fits within value types. And then we have reference types. So we have dynamic arrays. We have lists, and then we have mappings. Okay. So we have enums again, pretty similar. We have structs again, pretty similar. And so that's about it. Sorry to rush through this so quick. If I can, I will do some Vyper hands-on. Let me just do some real quick, just so you guys have at least been exposed to it. So first of all, actually my slides cover this. So in order to use Vyper inside Remix, you'll need to install a plugin. So when you first pull up Remix, it's going to look like this. There's no Vyper tab like you see on mine. You'll need to install it. So you go to the plugins here and just search for Vyper and install the one that looks trustworthy. And then once you do that, you'll get this new tab here called Vyper. You can, by default, it wants you to use a local compiler, and you're not going to have that set up. So select remote compiler, and again, trust it. And then, yeah, you'll be able to come over here and compile your code. Sorry to rush through that so quick. So let me go ahead and do something real quick. So I'm going to come over to Vyper, just make sure it's there. I've got my remote compiler here, okay? I'll just walk through it real quick. So you go over to the plugin manager, and then you just search for Vyper here, right? And then I've got it installed, so it's right there, but you'll see something there and probably like an install button or something like that. And that's what you'll need to do. And it should be pretty easy. Once you have that, you've got this tab. You come over here, select remote compiler. Okay. I'm going to come back here and then create a new file, and we're going to call this flipper2 dot, I think vi is the extension, and then let's see. So again, there's no class keyword, so we can just simply do a call it flipped is a uint 256, I think like that. I don't think I need that, and then I can do at external, and then we do def and it, no arguments, like that, and then we're just going to say uint, or we're going to say flipped equals false, like that, okay? And then we want at we'll call this one, yeah, at external, I think I have to do a new line, I don't remember, at view, and then we'll call this def is flipped. I think that's the, I think it's still camel case flipped. And then we return bool, okay? And then we just say return flipped, okay? And then we want one more at external, and this one is not view, def flip. Flip does not return anything, so we just do that. We say flipped equals not, I think it's not flipped. Okay. And then we'll come over here and compile, and definitely do not remember my syntax very well. So flipped is not a storage variable because I did flipped. Oh, self. I need self.flipped. Yeah, that's probably what somebody was trying to say. A question? Go ahead. Oh, yeah, good point. That is also true. So is it self or is it self? I don't remember. Self.flipped? Yeah. Okay, and then we need that here as well. So self.flipped, and then we need the same thing here, self.flipped. So self is basically like a this pointer, or it's like it's referring to this contract. And then we need this to be a bool. Okay, and then hit compile, and flipped is a storage variable. Access is as self.flipped. .flipped. Yep, thank you. All right. Team effort here. Okay, so we compile. Cool, we got it. Now we can come over here, and I'm going to clean up my contracts. And we got flipper2 here, so we can deploy it and come down here. We see it. Let's see, is it flipped by default? It's false, which we set in our init function. That's good. And then we flip it, check it again, true. All right, cool. Okay, and so I really quickly want to go over a couple other things. Back over here. So let's go to reentrancy. Okay, so this is the DAO hack. The DAO, again, was hacked, and the vulnerability was within this withdraw function. So I'm going to walk through it first as like a normal user would. And so what we do is we require that balances, so balances presumably is some like accounting thing where we've kept up with who's deposited what into the contract, right? And so we require that balances for the message sender is greater than or equal to 1 ether. That's all we can withdraw. It's just a limit they impose. So then we assign bow to the user's deposit, assuming we pass this. And then what we do is we do message.sender.call. So this is a way to call a contract. So remember, message.sender is the address type, and one of the functions on address is call. And so what we do is whoever sent us this, we're going to call and we're going to pass in this value, but we're not going to pass in any input data, and we're not going to specify a function. And so the intention of this was that it was just simply going to pass along some value to whoever called it. And then once we're done, assuming that it actually sent, then we update their balances to be 0. Okay, now I'm going to go back through it, but let's pretend that the person calling it is a contract called attacker. And we want to figure out how we can exploit this. So we have a contract caller, right? So message.sender is our contract, we have contract attacker. Message.sender is now our contract attacker. We come in here, and the first thing we need to do is make sure we have at least 1 ETH deposited. Okay, fine. So the contract now needs to be able to invoke this and deposit it with whatever deposit function it has. No problem there. And then so it's going to grab the balance for it. Now it's going to call us, which is the contract attacker. And so what we want to do is figure out if we can exploit this. So there's what's called a receive function and what do they call it? A default function, or I forget what they call it. A fallback function. Thank you. So nowadays those are two different things. So there's a receive function that can receive ether, and there's a fallback function, which is called when no other function argument, when you try to call a function that doesn't exist. And at this point in time, those were the same thing. And so what happened was this attacker contract can specify a fallback function. And so now this isn't just simply going to pass along value. It's going to actually call this callback function, default function. I forgot the name already again. Anyway, it's going to call the function. And so now our contract can, instead of just simply receiving the value, it can now do something arbitrary at this point. So what can we do? We can have this contract now immediately call withdraw again. And so what happens is we get through here, we check that we have 1 ether, we grab whatever ether is in our accounting, our mapping, and then we send it. And then immediately we go back up here. Notice that we haven't updated our accounting for the balances by this point. So we get here, we send the value, we get back up here, this is still greater than 1, we still have the same amount here, we send it again. And we keep doing this until we stop. And then finally, now here's what might have been a little tricky about implementing this. You can't revert, right? So you can't run out of stack space for one thing. So you need to make sure that you do this so that you drain this as much as you can. And then at the end, we need to faithfully let it finish and set this to 0. So probably then we need to go deposit some more and go back and keep doing this. So we're going to have to do this in an iterative approach. So that is the DAO hack. And remember, this is what split Ethereum into Ethereum and Ethereum Classic. So how can this be avoided? There was supposed to be a question, but here you go. Here are the answers. So one is just simply to do commit the state before we do the actual withdrawal. So if you simply moved this up here, problem solved. Of course, we also have some other tools, at least in, we have a couple other tools. So this is a re-entrancy problem. What happened was we re-entered this function in a way that wasn't expected when it was originally written. So we can prevent re-entrancy. So Solidity has the modifiers. We could write a modifier that prevents re-entrancy. And then we saw that Vyper has this non-re-entrant decorator, which we could have used. Any of these would have solved the problem. And we probably would just have one Ethereum today. And so I think this is the last bit that I have. I'm going to kind of rush through it. So it's really just a thought exercise. Can you store a secret on chain? And let me phrase that a little bit differently. If I want to verify a secret on chain, how would I do it? So can I store a secret on chain for starters? If anyone is convinced yes or no, go ahead.
So my answer is no. Even if you set the variable to private, that only means that it cannot be read by other contracts, but that code is going to be stored in many nodes. And as long as those nodes have a way, can infer how is your data structure stored in your contract, and using the bytecode to deploy it, they can find out that secret. So if I had to check a password, I would probably store the hash of a password in my smart contract or something like that.
Yep, that's an option.
Verify that.
Yep, okay. I saw another hand back here. Anyone else want to venture any input? Okay. Yeah, so we can't store a plain text secret in a contract. Obviously doing so reveals it. If I write it to the contract, the whole world sees it, it's revealed. So it's not going to work. Okay, so we can store a hash secret on chain. So if we want to store a password on chain or verify password on chain, we could store the hash of it. And then we could use it to verify some input. Okay. The problem with this is that as soon as we accept that input, we've revealed the secret, right? So the idea is that we store the hash of the password on chain, user sends in the password, we can make sure that whatever that is, we hash it and come up with the same result. That works, except that as soon as we see a transaction on chain, it doesn't even have to settle yet, right? As soon as we see the transaction in the mempool, now we know what the secret is. It hasn't even necessarily settled on chain yet, right? Somebody else could front run this. They could send the same transaction but with a higher gas price and get their transaction in first. Or a block author could totally censor it and just insert their own transaction in their own block, right? So that's not going to work. So there's a concept called commit reveal. We'll go over really quick. And this is sort of, I talked about settling on chain. I talked about it being revealed before it's settled on chain, right? And I think that's kind of the problem here. And so commit reveal kind of solves this by having a two-step thing. So what we do is we store a hash of a secret on chain. And then to reveal it, we do a two-step thing. So the first thing the user is going to do is they create a commitment. Now this commitment doesn't reveal the secret. So what we do is we hash the salt along with whatever they think the secret is, and they're going to store that on chain. Now we can make sure that that settles. We can let enough blocks pass till we are convinced, or maybe it finalizes. And at that point, we know who committed it, and we know what their commitment is. Well, we know what their commitment is, right? We don't know what's inside the commitment because it's a hash, but they can't spoof this commitment to be any other thing, reasonably speaking, than whatever they committed to. And so then they're going to have to do one more step at the end, which is a reveal. So they're going to take whatever they said their commitment was. So the preimage of that is the salt in their alleged secret. So they're going to provide us the alleged secret and the salt. Now we can verify that the alleged secret equals our secret up here. And then we can verify that the commitment is equal to the hash of the salt and the alleged secret as well. And I guess you could do one more step and have the password or something like that. But there's one other thing I wanted to talk about. You can obviously use public key cryptography. So one thing you could do is store the public key of something on chain, and presumably somebody's got a private key. Now you don't have to reveal the private key, obviously. They could just sign a message. So you could challenge them, and they could sign something, and you could verify that it is that they had the private key. So how does this compare to commit reveal? Well, it's a lot more flexible. So in commit reveal, we still had to reveal something, and that's kind of a one-time thing. Now, this is a lot more flexible. So if I wanted to verify that Bob is Bob, I could store his private key, and I could use it for all sorts of different purposes. Once we use it, we haven't kind of like burned through it. Okay, I think that's it. So does anyone have any questions? Question over here? Yeah. And then Jacob's got a question next, if anyone wants to throw him the other one.
Hi, I'm Richard. Can you just go back to the previous slide, please?
Yeah. This one or?
Maybe the one before. Yeah. So when you say salt, is that some sort of element of randomness?
Yeah. So anytime you have a hash, you take something and you hash it, right? If you change anything about the input to that, it's going to drastically change the output, right? That's the whole point of a cryptographic hash. So a salt is just a way to add some little bit of difference to it to completely change the outcome. And then that means that even if you know this, you've still got to know the salt as well.
Is the salt the same each time, or are there variants of salt?
The salt would be something that you keep secret as well until you want to reveal it.
Right.
And of course, if you use the same salt over again, you're going to introduce a replay attack, right? Yeah. So a salt in this case is very much like a nonce. You would call a nonce a salt. Yeah. Jacob.
My question has to do with Vyper. I don't know that much about Vyper, but in Solidity, sometimes if you make a function with too many local variables, you get the stack too deep thing, which is super annoying.
Yeah.
Does Vyper fix that, or is that a limitation of the EVM, so you can't fix it?
Yeah, you're exactly right. That's a limitation of the EVM. So the EVM specifies the stack size, and that's like a consensus thing. Everyone agrees on how deep the stack is, so you can only recurse too many times. But you don't necessarily have to recurse, of course, to exhaust your stack. You can put too many things on the stack, as you pointed out, or you might, in fact, you can actually use this as an attack. If I have a function that presumably is safe from a Stack Overflow, and I want to attack it, what I could do is insert enough garbage on the stack here so that when I call it, one or more of its variables is going to cause a Stack Overflow. It's going to revert, so that's maybe not a good like attack vector there, but in other cases, that can be an attack vector.
I see. My thinking was because it's kind of Pythonic, it's maybe ran through like a interpreter and then turned into Solidity or something that the EVM knows. So there's no way to fix this. There's no way to fix the stack too deep because it is interpreted, or is that just? Is that not?
It's going to compile down to bytecode just like Solidity does. Okay. So at the end of the day, you have to have bytecode in order to run it on the EVM.
Okay. And then you can't fix that.
Yeah, you can't fix a Stack Overflow. A Stack Overflow is something you just should not introduce, and recursion is the main way you get that. So you just have to be careful with recursion, and that's why they don't allow it or try to prevent you from it. Yeah.
Okay, thanks.
Question up here.
So is his question related with the Turing completeness?
Okay.
Of EVM? Yes.
Oh, sorry. What's the question?
Is his question related with the Turing completeness of the EVM?
Yeah, I guess. So when we talk about a Turing, we usually talk about like infinite amounts of resources, and a stack is not an infinite resource. So that is one of the limits that we impose that I guess makes it not Turing complete. But maybe you would say that's true of other programming languages as well. Yeah. Any other questions? All right. Well, thank you very much.
Thank you.